Hey guys, in this little video, we're going to do one of the more theoretical topics we did last year. And sometimes when it goes theoretical, takes a while to sink in. And that is the formal definition of the derivative. And it's two forms of expression. Okay, so just a quick little, do you remember? I guess, if you don't understand it, you'll get probably at most 1 or 2 points off on the AP test and on my test. It's actually really important. It's just we don't use the formal definition because we have all these rules that are so much easier. Like, I know the derivative of x squared is 2x, so why do I need to do the formal definition? But we're going to do it anyway. Okay. By the way, kind of like this. I want to show you what I mean. So in Algebra 2, whoops, better share my screen with you, huh? So let's do a screen share. There we go. And I forgot to start my QuickTime player. So now let's see if that'll work. Sorry. Okay, so I just want to show you something what I mean by the theory is important. It's just, for example, and I showed you guys this last year, but you learned in algebra and algebra 2 that this makes a parabola, and that the most important point on that parabola is the vertex. And they gave you a formula for it. They said, well, for you to get the x coordinate, you just do negative b over 2a, but that looks like magic to me. Like, why do I do negative b over 2a? I get why I plug it back in to get the y coordinate, obviously, but what did you just pull that out of your butt? Or like, why is that? And it comes theoretically from calculus. So, and I showed you guys this last year, but I wanted to talk to you about what I mean about the theory behind it is important. Without the theory, we wouldn't have this formula for our Algebra 2 students and Algebra 1 students to use for the vertex of a parabola. But in calculus, remember that this only works for a parabola. And what if we had a cubic and I wanted to know that, right? I don't do negative b over 2a. What I do is I set a derivative equal to 0 and find where that derivative equals 0 will find me where the horizontal tangent lines are. Well, on a parabola, there is only one horizontal tangent line, and it must occur at its vertex. So if I were to calculate y prime, or dy dx, remember, a in this scenario is constant, constant, constant. I bring the power out front and get 2ax to the drop at 1, plus the derivative of bx, or 3x, or 4x, or 5x is just b, and the derivative of constants always go to 0. Now, on a parabola, the vertex occurs where that derivative equals 0. So I'd get a negative b over 2a would have to equal x. When I'm solving this, that is the theory behind why we can tell our Algebra 1 and Algebra 2 students that to get their vertex, you just go ahead and just do negative b over 2a. But we can't tell them about the calculus of it because calculus comes later. So with the formal definition of the derivative, it came first, which makes it hard to learn when you learn the theory before you learn all those little shorter ways. But we have the formal definition of the derivative, and we have it basically two ways. So of the function and then at a point. So first we're going to talk about just like in terms of x. What is the derivative of x squared? Well, let's write that down. F of x equals x squared. And you're like, the derivative is 2x because of the power rule. But where does the power rule come from? Why does it work? Blah, blah, blah. It's not magic. All right. So this is what I mean for the first one. We're not doing f prime of 4. We're just getting a function for the derivative. So let's go back. Make ourselves a nice roly-poly function. And let's call this x. Let's put a tangent line on there. Right there at x. And I want to find its slope because I want to find f prime of x. Sorry, I was fixing some notation there. So watch what we do here. We say, well, I can't find the slope of a line with one point. Like, How do I do that? Right? I need another point. Well, I'm going to go throw one on here. So this green line right here, which has been scooted over, and we say it's get scooted over h or delta x. It depends on who's teaching it, your textbooks, the whole bit. But we now have these 2 points on the green secant line, correct? And if I were to write them, I'd say, well, this is x and the y value there. And this has been scooted over to x plus h. And the y value there. So f up. Sorry, my wrist keeps touching my iPad. That's why it is goofy. So that's a h, by the way. Came out a little funky. So let's clean that up. We've got nothing but time, right? So there we go. Now the slope of that green line is certainly not a very good representation for the slope of the tangent line or the red one. But let's write down what it is. All right. So if I would just say, hey guys, what's the slope of the green line? Algebra 1, change in y or y2. This guy. Minus y1. This guy. Over change in x, x2. This guy, x plus h. Minus x1. So this is an expression for the slope of the secant line, or that green line, which is actually way too gradual for the slope of the red line. But when I write it a little nicer, it becomes f of x plus h. I should do it in green. It becomes f of x plus h minus f of x all over h, right? But this is what I'm going to do. I'm going to say, well, why did I put it so far away? That would have been better. So what I'd really be doing is taking this h and, scooting it just to right here. That would be better, right? But it would be even better if I scooted it even closer. So let's grab that eraser and scoot that h so it's just like over here in x and x plus h, right? But why not get it as close as possible to x, okay? So that what happens is h will be approaching 0, right? As h approaches 0, I'm collapsing on x there, and I'm collapsing upon getting the slope of the tangent line. So it becomes a limit as h approaches 0 of this, okay? The slope of the secant line. H can't equal 0 because then my slope would be 0 over 0. Wouldn't you agree? Right? F of x plus h minus, f of x. When I plug that 0 in for h, I get f of x minus f of x 0 over 0. So it can't be 0, but we're going to get so close. We're going to get to 0.0000 to croak over and die and hand it off to somebody else. And we're going to basically be there, right? This right here is the formal expression for the derivative. Okay, now watch. Let's go back up to my x squared, which I know the derivative is 2x because I've been taught the power rule, and I'd always do that. What's the derivative of x cubed through x squared? Done. But watch me do it with the formal definition. Okay, so I will arrive at this 2x using this definition. It does work. We just don't use it because we have shorter ways now. For example, for the vertex of the parabola, you're not going to constantly be setting the derivative equal to 0 when we know it's negative b over 2a, right? So let's go use this formula. If f of x is equal to x squared, right? That'll go right here. F of x plus h, when I put it in there, will equal x plus h, quantity squared. When you FOIL that, you'll get when you FOIL that, you'll get an x squared plus xh, so plus 2xh on the OI of the FOIL, plus h squared, right? So now watch when I write, this is called a difference quotient, but watch when I write it. I have the limit as h approaches 0 of f of x plus h, this guy, x squared, plus 2xh plus h squared, minus f of x. F of x was x squared, all over h. Gone, gone. Factor the h out of the top, and you get 2x plus h. And I'm right here, factoring that guy, all over h. The h's cancel. I plug 0 in for h, and la-di-da, I got 2x. So what's the derivative of x squared? 2x by the power rule, 2x by the formal definition of the derivative. So often with this, you'll never have to do it because we know how to do the product rule, the quotient rule. We know how to do all the rules that allow us to avoid this. But what College Board will do is say, give you the formal notation, and that's usually pretty clear when you see this h approaching 0 here. It's usually pretty clear that that's what we've got going on. So and you'll see like some functions. So let's do, say, natural log of x plus h minus natural log of x over h. All right, so again, when you plug in 0 for h, you get ln x minus ln x, which is 0 over 0. This is the formal definition of the derivative of. In this case, my f of is the natural log function. My f of x is the natural log function. They'll always have ln x as one of the options. This is not ln x. This is the derivative of ln x. Okay, this is f prime of x. All right, so f prime of x equals f of x was ln x. So what's the derivative of ln x? 1 over x. Now, you could outsmart this a little bit when it's asked like this because we now have a L'Hopital's rule that says for a limit, if you have a direct plug-in that results in the indeterminate form of 0 over 0, you can just do the derivative of the top over the derivative of the bottom. So as h approaches 0, when I do the derivative of the top over the derivative of the bottom with respect to h, right? You could outsmart it with L'Hopital's rule, but I kind of like that. The other form is, did I label that an A here? Yeah, I did. So the other thing is, and we didn't use this hardly at all either because this is way easier to do L'Hopital's rule on, but it's the formal definition of the derivative at a point. So for example, what's the derivative of x squared at x equals 3? And you'd say, well, the derivative of x squared is 2x at x equals 3, it's 6. But there's also a formal definition for that. And it falls out similarly to that other one. It just looks a little different. So let's go to a point. Let's go to the point 3. 3 comma f of 3. So I don't want the derivative everywhere. I don't want a function for the derivative everywhere. I don't want to know what's f of 3. Or sorry, f prime of 3. Well, f prime of 3 would be the slope of the tangent line, and LaRue should have drawn it better, but I'm getting tired. I've made a lot of videos today. This is very time consuming, by the way, to do this hybrid system well. I have to myself, like, don't just get the task done, do it so they learn it kind of thing. So it does take a lot of time. Anyway, I'm just getting sick of making videos. I'm not sick of you guys. I love you guys. All right, so here we go. We have x, we have f of x. I want to find f prime of 3. I want to find the slope of this red line right here. What is it? Well, I'm going to follow a similar process to what I did on that last one. I'm going to grab purple. I'm in a purple mood. I'm going to move over here and just say, well, here's some other point on the curve. Right? Now I have a purple line that looks nothing like the red line, but I'm going to squeeze it up on it. And so I'm going to take the slope of that purple line, which is f of x minus f of 3, change in y, over change in x. But I would really like x to creep up on 3, right? So that purple line creeps up and gets closer and lands basically on top of the red tangent line, or becomes the slope. So what I'm going to do is take the limit as, not as h approaches 0, because this is, I'm squeezing x specifically at 3. I'm going to get the derivative at a specific spot. So this equals the derivative. Now take a look. If x is 3, I get 0 over 0. If I L'Hopital this, right? If I were to L'Hopital it, I would get 0, 0, f prime of x over 1 at 3, f prime of 3. So this is formal notation for the derivative at a point. So let's test it out with x squared. F of x would be x squared. F of 3 would be 9, right? Over x minus 3, I'm going to take the limit as x approaches 3. Now, you would never do this because we know the derivative of x squared is 2x. Sorry, I've got linkage. So f prime of x is 2x. So f prime of 3 is 6. It's as easy to be like, why would I go through this? You wouldn't, right? But I want to show you the theory. So if I plug in a 3 right now, I get 9 minus 9 over 3 minus 3. But x minus 3 cancels. So I actually just get the limit as x approaches 3 of x plus 3. So I actually just get 6. Pretty cool, right? This one we focused on hardly at all, like maybe for like 10 minutes, one of the first days in derivatives, because I knew that you would eventually not use it, and you still won't. I knew that you would go to L'Hopital's rule. So even if you saw like the limit as, let's say, x approaches pi over 2 of cosine pi over 2. Sorry. Let's do cosine x minus cosine pi over 2 of x over x minus pi halves. On a direct substitution, going to 0, I knew you would go to L'Hopital's, and you still should, to be honest. I just wanted to show you how theoretically it works as well. Because when you L'Hopital, the derivative of a constant is 0, derivative of a constant is 0, derivative of x with respect to x is 1, derivative of cosine is negative sine x. At pi halves, we'd have negative sine pi over 2, right? Sine pi over 2 is 1, we get a negative 1. That's the derivative of f of x at pi halves. Hopefully that helped a little bit. I don't know. The thing behind the theory, like I said, is it's really great if you understand it. It's great to recognize it, but you'll never have to do it. So that ends this guy. So let me do a stop share, and you guys have a good one.